Hello student, let's us work on the problem number 2 of the extra problem. In this problem we have the simple beam. This simple beam has the pin support on the left and the lower support on the right, and the section is here and it has the area of 700 square millimeter. This is structural steel section, and the I sub x of 513,333 millimeter. If also you like to have this in the meter power 4, that means you're going to have this one, let's say 10 power 6 millimeter power 4. 1, 2, 3, 4, 5, 6. Okay, and if you like to make it to be meter power 4, you got to divide this one by 10 power 12. The factor of 10 power 12 come from what? You know that, right? Okay, that is going to be 333, 10 minus 6 in meter power 4. And this beam is going to subjected to the loading of 3 kilonewton per meter. By doing this, they ask us to determine the internal force and the internal moment that occur on the section AA. That means they ask us to determine this. Before we can find the internal forces and internal loading, we got to draw the free body diagram of the beam, and then we will find the reaction first. When we find the reaction, we can find the internal forces and moment. By doing this, that means we got to draw the free body diagram of the beam. Is going to has, let's see, this is A, B, this is C, this is D, under the application of distributed load given here of 3 kilonewton per meter and has the X and Y reference axis. You will get this for the D sub Y, this for the C sub Y, and this one is for the C sub X. And you can see the equation of X sub X equal to 0. C sub X for sure is 0 kilonewton. And then if you can see the loading and the structure is in symmetry, you can see the C sub Y and D sub Y gonna be equal. You can prove it easily. Summation of the moment at C equal to 0, and you can see the beam is 2.0 meter long. So this D sub Y is going to rotate counterclockwise about C. So you got to have D sub Y times 2. And then what? And then you get this one equal to, this is going to be the resultant of the uniformly distributed load. That is going to equal the area of the uniform load. That is going to be 3 times 2. That is going to be 6, right? That is going to be, no, not 2. This is 1.60 meter. This is 3 times 1.6. 3 times 1.6 is going to be 4.8 kilonewton. That is going to be 4.8 kilonewton. So this one is going to be clockwise rotation. That is 4.8 kilonewton. And then time this distance, a half of 1.6 is going to be 1.6 divided by 2. Okay, and then by doing this, you will get D sub Y. Putting them into this is going to be, this is going to be 4, this is going to be 0.4, and then that is going to be 2.4 kilonewton. And then if you do the summation of F sub Y equal to 0, C sub y plus D sub y. This is 2.4 kilonewton. 2.4. That is going to be equal to 4.8 kilonewton. So your C sub y is also 2.4 kilonewton. This occurs when the structure is symmetry. The reaction on the left and reaction on the right, they are going to be equal. Okay? And then next, we are going to cut this section. We cut this section at section A, B, and the beam subject to what? Subjected to 3 kilonewton per meter. We have this one, this one. We cut it at 0.4 millimeter. This is 3 kilonewton per meter. This is 0.4 meter. And then you have this one for 2.4 kilonewton. And by cutting this, that means you're going to have this one for the moment M, and the shear here is V. Okay? And second, by the free body diagram of the section okay, here is a A to B. Okay, and then what? And then phi V and M. Next we can find the shear and find the moment. Then we have summation of F sub y equal to 0. Downward is positive, so V is downward. This one will have the resultant force again equal to area. That is going to be 3 times 0.4. Then it's going to be 3 times 0.4. That is going to be 1.2 kilonewton. And then this is going to be downward, right? In the same direction of B. This is going to be 1.2. And the upward is 2.4. That is 2.4. So we have the V equal to this one 2.4 minus 1.2. This is going to be 1.2 kilonewton. That is for the shear here is going to be 1.2 kilonewton. Then you do the summation of the moment here equal to 0. The counterclockwise moment is positive now, so our moment take here, and then it's going to plus 1.2. The distance here is half of this. That means it's going to times 0.4 divided by 2, and then that's going to be equal to what? This is counterclockwise, this is counterclockwise, this is clockwise, 2.4, and then times the distance here of 0.4. Okay, by putting them together, we will get the moment of 0.72 kilonewton meter. Okay, that is going to be 0.72 kilonewton meter. Then they ask us to use the equation that they given me from the chapter 7, from the chapter 6 to determine the normal stress and also to determine the shear stress. Okay, we're going to have this normal stress. This normal stress is only due to the moment, and they are asked us to looking for the shear stress. This is shear stress going to be from this at what? At the point B. At the point B. Only at this point. Okay, as the point B. Anyway, I think it's better for us to draw the shear stress and normal stress distribution, because below this they also ask us to draw the normal stress distribution and also the shear stress distribution on this section. Anyway, due to the space limited here, I will draw the section and draw the stress distribution in this portion, okay, to make things more clear. Okay, this is 4 centimeter or 40 millimeter. Let me put put this one in the scaling. Let's put this one for 2 centimeter. That is going to be scale of half of this. This is 4, this is 2. This is going to be 40 millimeter. And the thickness of this 5 millimeter, this is going to be 5 millimeter. That is going to be the top portion of this section, or this is top flank. And then it also have the web. Okay, the web is going to be 4 and 2. That is 6 centimeter. Half of that, let's put in 3 centimeter like this. That is going to be the portion of the web. And then we may put this one as the bottom portion. Okay, this is the flank. This is the outer section. This is going to be 5 millimeter. And this is going to be the total of 60 millimeter. This is 6 centimeter. Okay, this is half. And then the total of this length now is going to be the total of 70 millimeter. Okay, and we can see this is going to be the middle part of the neutral axis of our section, and this is going to be the centroid of the section. Basis upon this, that means we have this one for 30 millimeter and this one for 30 millimeter for this one. The webbed separate into 2 parts, and then based on the section that we are understand here, the section subjected to what? Subjected to the positive moment. That means what? That means it's going to have the compression on the top, and it's going to have the tension on the bottom, and in between the stress is gonna be in triangle. Why we know this? Because the stress that occur here is determined from the moment time what? Time the distance y and divided by the moment of inertia. Since the I is constant for a given section here, and also M is constant for a given section here. So the value of stress vary with the distance y. So this is the linear function. The top is going to be in compression. The bottom is going to be in tension, and it has the linear relation. What we have is this one, the stress on the top and the stress on the bottom, they must be equal because the distance 35 millimeter, the distance 35 millimeter, they are equal. This is going to be in compression. This is going to be in tension. This is also going to have maximum compression. Okay, this is going to have maximum tension. Okay, and then the B. The B is what? The B is 20 millimeter. That means if you like, this is 30 millimeter. The B is somewhere here. This is going to be 20 millimeter. Measure from this one. Okay, and that means what? That means the top portion is this is 10 millimeter, and we can say that if we consider this, the B can be somewhere that you put the portion. It's going to be here, and the stress occur at this point is going to be sigma sub B. Measure what? Measure only 10 millimeter from here. Okay. Okay, if we understand this, we can determine stress at the point B. Sigma sub B is equal to the moment around here is 720 Newton, and then divided by the I. The I is here, we already computed, is 0.51 to the 3, 10 minus 6, that is 0.51333 10 minus 6 meter powerful. And then this is what? This is 10 millimeter. This is 10 millimeter. So this is going to be in meter, 0.010 meter. You put this one into your calculator. You will get the stress here of 14.03 megapascal. That is the value of this is 14.03 megapascal. Okay. And also, if you like to find the sigma max, can you find the sigma max here? Sure. You measure from this point to this point for the y. That means that is going to be 30 millimeter and 5 millimeter. That means you're going to measure for 35 millimeter if you like. Okay. You also can use the triangle to determine it. Okay, anyway, just put this one, sigma max, that's in. It's going to be the same thing, 720 Newton meter. Now, the I still there, 0.5133310 minus 6. And the distance is 35 here, so it's 0.035 meter. If you put this one, you get this one for 49.1 megapascal. So this one going to be 49.1 megapascal. Or if you prefer, you may use the triangle. Okay, since you looking for what? Looking for sigma max here. You can see sigma max here divided by this length divided by half of this. So by using the slope, you will have sigma max divided by 35, and then it's gonna equal to what? It's gonna equal to sigma sub b. Okay, sigma sub b is 14.03. This is the full divided by 10. Okay, if you put this one into your calculator, you will get the sigma max equal to 14.03 divided by 10, and then you times it by 35, and then you should get this one for 49.1 megapascal. So the value of sigma can be determined first by Flexure formula, and then the other point due to is in the triangular, so you can use the slope to determine the stresses at the other point if you like to determine them. It's really easy and convenient to do so, right? Okay, and then you have what? You got to consider the transverse shear stress by doing this. The section is going to this one like this, and then again, like I put it in, I said it many times, the stress distribution for the I section is going to depend on a lot of things. The first thing is the equation that's used to determine it is tau equal to VQ divided by IT. Okay, on a given section, the V is going to be constant. Okay, the I is going to be constant, and then the Q and T going to be vary depend on this. And if you consider this section, the joint between the web and the flank have the different width. That means what? That means if you compute by using this equation, the Q will depend on what? The area here. Okay, so the moment of this area about the centroid of the section, the Q going to be constant. So the stress between this point is up to the width of the flank and the width of the web. Okay, that means what? If you divide it by the flank, the value of this gonna be small. Okay, let's say this is going to be tau 1. And when you divide it by the width of the web, this value going to be get larger. And this one is what? This one is 40 millimeter. And this one is only 5 millimeter. This one is only 5 millimeter. So the value here is going to be what? 8 times different. So this is going to get larger. Let's say this is going to be tau 2. Okay. And then the value of shear stress of the section will increase in the parabolic manner. And again, the tau max occur at the neutral axis. Okay, that is going to be tau max. Again, due to the symmetry of the section, the top portion and the top portion, what we have is the stress distribution on the top portion. That is going to be tau 1 must be equal. This is tau 2 must be equal. And then the other portion, we will have this in the curve in the parabolic shape. Okay, for the shear stress distribution on this section, there you or me as got to determine tau sub 1, tau sub 2, and tau max. And this time they ask us to determine the tau at B. At this point is what? At this point is the point that we consider the section only in this point. And what we have from this is we set this one as the point B. And what we have is the tau. The tau sub B is going to compute basis on the shear here, 1,200 Newton. And then again, it's going to divide it by the moment of inertia 0.151333 10 minus 6. Okay, and this is only what? 5 millimeter. So the divider of this is going to be what? 0.005 meter. And the last one that we are looking for is going to be what? The Q. Okay, we should separate this section into two portions. The first one is this one, and the second one let's put into this one to determine the tau at this important, this asking point. And the Q is what? So this is this length. You cut it here. This is only 20 millimeter. And the width of this is only 5 millimeter. So the first one you will have 0.005. And then time what? 0.02. And then this is what? This is the centroid of this section. And then you got to take the moment of this section about the neutral axis of the section. So what we have is what? What we have is the distance here is 10 millimeter. And this is half of 20. This is 10 millimeter. So the total of this going to be 0.02. So it's the O2. This is the distance between centroid of this area to this. And you got to plus this one by the orange. This is 40 millimeter. And this is 5 millimeter, 0.04. And then 0.005. And then the distance here measure to the neutral axis is going to be the moment arm of this. And you know half of this from this to this is 30 plus 5. This is going to be half of this. This is going to be what? The total is going to be 35. And then you got to minus this one by half of the thickness. So this is minus by 2.5. Okay, then this one going to be 32.5 millimeter. So the last one, you're going to have 0.0325. And then you put this one into the calculator. You're going to have sub B of 3.97 megapascal. Okay. And then they ask us to draw the stress element at point B. At point B. At point B is subjected to what? This is the normal stress. It is subjected to normal stress. You have the normal stress in this direction. It's in tension because it's in the bottom portion in tension. This is 14.03 megapascal. Okay. And then the shear is downward. That means what? That means this stress is downward. When this one is downward, it's going to have this one upward. And if you take moment here, this is rotate this way. This is gonna rotate this way. And we have this one to balance this one. And we have this one for the tau. We have this one tau sub x, y, because we said this one is x, this one is y. The tau is in both direction. And then this one is going to be 3.97 megapascal. And this one is what? Sigma sub x equal to this one. This one is in tension. Okay, that is going to be the stress element at point B. And if you go further, they like us to draw the normal stress distribution. Okay, this is finished already. Sigma max here is 49.1 megapascal. And this is 0. And this is compression in 49.1. And then they also ask us again for the stress distribution. Now, is this the question? What is the tau sub 1? What is the tau sub 2? The tau sub 1 there is also tau sub 1 here. The tau sub 2 here is going to be tau sub 2 due to the symmetry of the section. Okay. By doing this, they ask us to indicate the stress. For this is okay, maximum and minimum. Okay. For this one, the maximum is here. Even though you know the maximum, you still find the tau sub 1 and tau sub 2. Okay. This is start by what? Let us start by find the tau sub 1. Okay. If you like to, tau sub 1. Tau sub 1 is what? Tau sub 1 is based on the computation of the V Q over IT of this area. So this is going to be the same thing, 1,200 Newton. And then divided by what? Divided by the same thing. Divided by I. Okay. And then divided by I. And then what? Tau sub 1 is based on the flank. Tau sub 1 is based on the flank. Okay. That means we're going to have the width of the flank. So the width of the flank is 40 millimeter. This is 40 millimeter. So this is 0.04 meter. Okay. So the Q of this green and the Q of this yellow, they are going to be the same. So the area here, 0.04 times the thickness, 0.005, and then the distance from this one to this one, right? So it's going to be what? It's going to be 0.0325. So this is 0.0325, and then you just close this one. And then you have this one for what? For tau 1, 0.379 megapascal. 0.379 megapascal. See, this is a lot smaller than this one at tau sub b of 3.97. Anyway, the next one, you got to determine tau sub 2. Okay, tau sub 2 is based on the width here. And you can see the ratio of the width. This is 40. This is what? This is 5. Okay, you may see this is can be computed by 0.379 and then times 40 divided by 5. You can compute this one easily. Tau sub 2 is going to be 3.064. This one is supposed to be 3.064 megapascal. That is 8 times larger. Ajahn, I don't believe it. If you don't believe it, you do the calculation as before on the top, just to change this one into the thickness here of 0.005. Everything here the same, here the same, Q the same. You will get the same answer here. So it's up to you. Okay, you may put this one 1200 times the same value here, and this one also 0.51333 10 minus 6 and the same Q. See, there are only the difference between this portion, and the width of this portion. Okay, and the last one, we kind of need to compute the tau max. When you compute the tau max, what we have is you got to compute based on this total area. Okay, so same thing, tau max still come from the same thing. V the same 1200 Newton divided by the same thing, the I is 0.51333 and then 10 minus 6 meter power 4. And here the width is only 0.005, so 0.005 meter. So the Q. The Q here, the Q for the green and the Q for the yellow is the same thing. Okay, you just put the same one over here. That is going to be the area 0.04 times the width 0.005 and then times the distance here 0.0325, and it's going to plus for what? The area, the pink area 5 millimeter and 30 millimeter 0.005, and this is 30 millimeter, so this is 0.030, right? 0.030. Okay,ถูกต้อง sorry, it's correct. 0.030, 0.005, and then what we have is this one is the centroid of this pink area measure to the neutral axis of the section. That is half of 30 millimeter here. So it's going to be what? It's going to be 15 millimeter. So it's going to be 0.15 meter. You put everything together, you get tau max equal to 4.116 megapascal. Okay, that is what should we have for this portion. Okay, I did drawing the normal stress distribution and shear stress distribution into this. And if you may recall, sometimes the maximum shear, they just ask us approximately to determine from the V divided by the area of the wave, Okay, if you take a look at this one total is 60 millimeter. This is going to be 60 millimeter. The thickness here is going to be 5 millimeter. The tau max can be approximate to be what? To be this one is 1,200 Newton, and then divided by 60 and times 5 millimeter square. You cut this one, okay, and 6 cut this one going to be what? 120 divided by 6, this one going to be 20, and then it is going to approximately 4.0 megapascal. It can be approximate like this for this section. Okay, that is everything that we like to have: the normal stress distribution, the shear stress distribution, the maximum, the minimum, and some important the stresses as the important point. Okay, and I also ask you again to draw the stress element. For example, at this point, let's say if this one is going to be 10 millimeter, okay, and this is 5 millimeter, what is going to be the stress element here? That is for your quick assignment. Okay, let me finish demonstration of solving this problem here. Have a good day.